Good afternoon, all.
Just 1 minute, ma'am. 1 minute.
Yes.
Okay. Good afternoon, all. So myself, Bashim, one of the placement coordinator from EC department. So welcome you all for the 4th week placement coding training on data structures. So this is the 4th week, and we have already 2 week sessions covered by Dr. Ram Prasad, and already 1 session completed by our Professor Sivasankari ma'am. So now it's a 4th week, and this is a 2nd week session for Professor Sivasankari ma'am. So Sivasankari ma'am she's already doing her PhD in big data analytics. So last week we have seen many topics and many hands-on sessions also we have seen. So this week also we are expected to do many sessions. So please listen to the talk. Okay. So you are expected to any doubts, any clarifications, please be more interactive. So placement sessions, as I think placement session full-fledged mode, it will start by July only, June or July. But many companies also started to want to come by April, like internship-based companies. So you should start working on your skills. So the data structures, if you want to place in good software-based companies, definitely you need a good skill on data structures. Okay, already you have completed some of the training with CCC. So apart from that, please try to gather more knowledge to get more company, like more super dream companies, marquee companies. So all the best. I welcome Sivasankari ma'am. Thanks ma'am for accepting our invitation and spending our. Thanks ma'am. You can proceed.
Good afternoon, students. So as said by sir, already we have covered the fundamentals. So for the past 3 weeks, you might have been learning about the array concepts, linked list concept, stacks, and queues. So today's session, we will concentrate on the tree data structure. So I will share the screen. I will first give introduction about the tree, and then we will go for the what is the use of the tree term, like binary tree. You have binary search tree, you have Avl tree. So in what way it is helpful, how it is going to save the time. So after the construction, we'll also discuss the time complexity associated with the tree functionalities. I will share the screen. Is the screen is visible?
Yes, ma'am.
Okay, thank you. Yes, students, just be interactive, because the first part we are going to discuss some of the basic terminologies only, because the first session when we discussed about what is a data structure, types of data structure like linear and non-linear, we discussed about this tree. So already we discussed like why it is called as a non-linear data structure. So again, I'm just repeating with the introduction part. If you have any doubts, you can just stop me in the middle. You can unmute yourself and you can ask your doubts. So it's a hierarchical structure. So it won't be having the elements stored in the contiguous memory allocation, right? So it's a non-linear data structure. So in a tree data structure, so how, yeah, this is an example. For example, you can see a tree here. So here you have the data represented as a nodes, and you'll be having the edge connecting these nodes, right? So can anyone tell me what is the root node in the given tree? You have nodes A, B, C, D, so on up to K. So what is the root node?
A.
Yeah, A is your root node. Okay, so these are some of the basics that you have to know. So okay, which node we call it as a parent node?
For B and C, A, and D of B.
Yeah, you're right. So in general, according to the basic tree terminologies, the first node that you have encountered in a tree. So as you said, yes, A is the first node. So this node, we call it as a root node. So every tree, if you have instead of empty tree, even you have a tree with a single node, you should have a first node. So that is always called as your root node. So similarly, So the edge. So for any node, like for example, the connectivity between the nodes. So the connectivity or the link that we are going to make, we generally term it as the edge. As the terminology, just we represent as link or edge. Similarly, nodes A, B, C are called as nodes or vertices. So here, so what is a parent node? Here you told A is a parent, B, C, E, G, yes. So all these are parent node. So how we are identifying the nodes as a parent node?
Those who are connected between two nodes.
Those who have children nodes.
Yes, yeah.
When a particular node will have branches, that's when we can call it a parent node.
Yes, the nodes that are having children, right? So the nodes that are having children, we generally call it as a parent node. Then what is a leaf node? In the same diagram, you can check.
I and J are the leaf node for E, and K is the leaf node for G. G and H is leaf node for C. Just like that, D, E, F is leaf node for B, I guess.
Yes. In general, so here in this particular tree, D, I, J, F, K, H are the leaf nodes because they do not have any children. So this is the last level. So that is a leaf node. Okay. So this is some of the basics. Child. So if you have a parent node, child is a descendant of any node, we call it as a children node. So similarly here B and C are children of A. Similarly, D, E, F are the children of B. Similarly, G and H are children of C. So like that, you can just understand what is a child, what is a parent. Then what we call it as something called siblings. I will show the diagram, then you can, sorry, I'll show the picture of that particular tree, then you can easily highlight. So what we call siblings, nodes belonging to same
Parent.
That's all. So here in this particular tree, we can tell B and C are siblings because they are going to have a same parent E. Similarly, D, E, F are siblings. Similarly, G and H are siblings. In the same fashion, you can see I and J are the siblings because they are going to have a same parent E for I and J. So in this way, we can identify the sibling nodes. Leaf node, just now we discussed. So the nodes that do not have any child, then we call it as a leaf nodes. So there are other names. We can call it as a terminal node, or also sometimes we call it as a external nodes. Some of the other ways that we will use to call the leaf node. Okay, so again, these are some of the simple terms. So if we call internal nodes, at least the node should have at least one child. Then that node is called as internal node, otherwise called as non-terminal. So here you can see A, B, C, E, G. So a node containing at least one child, we call it as a internal nodes. These are the basics. So I'm going fast. If you want me to go slow, then just let me know. I will move to the slides very slowly. Okay. So how will you determine the degree? So whenever we have a node, if we want to calculate a degree of a particular node. So degree is nothing but the total number of connectivity, right? So for example, here from B. So let us, again, this is not restricted. We will be having in degree, out degree. So the number of, depending on the direction. So here in this tree, so degree is represented as the number of children according to this manipulation. So the degree of A is 2 here. So he is having a children B and C. Similarly, of degree of B will be 3. And similarly for I and J and all, you cannot have a degree, it will be 0 based on the number of children it is going to have. And the next one is level. So these are the things we will be concentrating when we move to the higher end. Like when we start constructing the tree, we will be using these terms like how to trace the nodes. So we should know what is the level of the each and node. So each and every level is nothing but the every step. So every step from top to bottom. So the A belongs to the first level, say starting from 0 to n-1. So B and C are the nodes that belongs to the level 1, and so similarly in the same fashion. So these are the level 2 nodes, and the last one I, J, K will be a level 3 nodes. So step by step, we can increment one level, and these nodes will be belonging to the pertaining to the each and every level. Okay. So coming to some of the important factors, because when we talk about time in the coming session, so we'll be talking about the time complexity. So this height plays an important role. So first we have to know how to calculate the height of every node. So for example, here in the same tree, if you want to calculate height of each and every node, right? So how will you calculate a height? Height will be calculated from
Number
bottom
of
to, yes, ma'am. Yeah. Yes, I got some answer.
ma'am, number of ages.
Yeah, so bottom to top and number of edges, and up, and also you have to make sure when you take the number of edges, also make sure you are considering the longest path. So I will tell you what is the longest path. Maybe as of now for this tree, it is very simple. You can see here I, J, K, there is no, from the bottom it is very, there is no children, like it's be 0, but whereas G, the height will be 1. For the C, the height is okay. Yeah, here there is a question. If you take C, right, you have height 2 or 1. So here there will be a confusion. What is the height of C? You told number of edges from bottom to top, right?
Ma'am, two.
Why 2? Maybe if you check the right hand side, I have only 1 edge, right? Why you are not taking 1? You are telling 2. Why?
Longest edges, right? From
Yeah.
down.
Yes, so that is the important thing. So any node you take, you have children, you have a path this side from G to H. Also, you have a path via H. But when we consider height, so you have to always take the count of the longest path. So in that way, it is not 1, it is 2. So comparing 2 and 1, the total number of edges in left and right, the highest value, maximum value, we have to consider. Similarly, for A, the height is 3. In the same fashion, the rest of the nodes heights are calculated. So it is a standard thing. Always the height of leaf nodes will be 0. And what is the, how will it, okay, this is the node wise height you are telling me. If I ask you what is the height of this entire tree, then how you will calculate the tree height, total height. You know, height of node B, height of node E, and so on. So in general, the total height of the tree is represented as based on
Longest node?
Longest node.
so the height of the root node is equivalent to height of the tree. Am I right?
Yes, no.
So whenever you take the root node height, you will be calculating the longest path from bottom to top. So that is equivalent to your height of the tree. That's all. So I can tell this tree is of height 3. Similarly, depth. Depth of the tree is the reverse. It will be calculated from top to bottom. So the same tree, if you want to calculate depth, so the depth of A will be 0. So here the vice versa. The root node depth will be 0. Whereas in the previous case, when we calculate height of a tree, it is from bottom to top. So leaf node height is 0. Whereas when you want to calculate the depth of that particular node, so you will be calculating the value from top to bottom. So you can see in the same fashion. So the top root depth will be 0, whereas B and C will be 1. And similarly, you can see the leaf level. So the leaf level will be, again, based on the longest, it will be having the 3 as a depth. So from the root to the leaf in the longest part, we'll be calculating the total number of edges. That represents the depth of the node. So the depth of the entire tree can be easily calculated based on the longest path. That's all. So whenever we are talking about path, continuously we are using this term path everywhere. So path is nothing but if I want to reach maybe in the same tree, if I want to reach, what is the path to reach, for example, E or path to reach F. So I can easily tell from root to that particular node, the sequence of nodes that is going to nodes and edges that is going to connect. That is the path. So path from one node to another node can be easily calculated. So here you can just manipulate here. Yeah. So if, for example, you want to know the path from J, so you can easily trace from root node. So A to B, B to E, and E to G. So this is the path between A and J. Similarly, if you want to manipulate, what is the path between C to K? So it is the sequence of nodes and edges that connects the two nodes. So here C to G and G to K is the path between the node C and K. So these are some of the basic terms. Again, the next term, subtree. So whenever you have a tree, you have your left or right branches, right? So this consolidatedly, we will call it as a subtrees. So tree is just a combination of multiple subtrees. Again, for this particular tree, again, you can divide it into the subtrees. Just it's recursively, you will be doing this process. So how we can represent tree? So we have methods to represent the tree. Either we can go for list representation or we can go for left child, right sibling representation. So these are mode of representing the tree, general trees. Okay, like we can represent, okay, the connectivity list representation, okay, from A, then you can just connectivity using the normal list. Or if you are going to use the left child, right sibling, you can have when you have studied, I hope everyone studied linked list. So in the linked list, we are going to have the data field and the address field. So like this, you can represent for the left child, right sibling. So you have the data stored, and for regarding the address, you can store the address of your left child pointer, maintain a left child pointer. Also, you can maintain a right sibling pointer. In this way, also you can represent your trees. Some of the modes, there's some of the modes to represent your tree data structure. So these are some of the basics. So when we are very specific about the trees, what is a binary tree? From the name, I'm not asking the exact answer. From the name, you can judge. So what is a binary tree?
Which has two branches.
Okay, which has, okay, in the other words, two children, right?
Yes.
Okay, two children. Can I have 3 or 4 more than 2 children in a binary tree?
No.
No, ma'am.
Okay, can I have 0 or single children in a binary tree?
Yes, ma'am.
Yeah, that is allowed. So when we go moving forward from tree to a binary, so tree is a very generic, right? So by telling tree, it is not necessarily, there is no constraint how many children you have to have. We can have 2 children, 3 children, up to n children you can have. So that is a generic tree. That's all. When you're very specific towards the tree, so the binary tree, maximum 2 children is allowed. It is not necessary. It is, yeah, you can see here. So this is an example of a generic tree. So whatever we have discussed so far, it's a generic tree where you have A is having 2 children, but you can see B is having 3 children, right? So this is a normal tree, normal generic tree. That's all. But we are specific about binary tree, maximum it can have 2 children. That means you can have a tree with a node with a 0 child or single child, 1 child. But maximum allowed up to 2 child, not more than that. So this is not a binary tree because you are having a node is having 3 children. So this is not a binary tree. So binary tree is something a special type of a tree. That's all. It's going to have this property. Again, in more specific, there's something called as binary search tree. I will tell you why we have to learn all these things. I will help you with the time complexity. Maybe I'm just opening the Jamboard. You just let me know whether you are able to view that because I have shared this. I don't know whether everything is visible or not. Is this Jamboard is visible?
Yes, ma'am.
Yes, ma'am.
Okay, then fine. So when we are talking about when we are talking about a general tree, we have discussed any node. So any node 1. So general tree representation. So you can have, this time writing the node value node 1. I can have any number of nodes, right? So n2, n3, and so on. There is no restriction for a general tree up to some n values. Okay. So moving on to the binary tree. So maximum 2 child. So this is a binary tree. That is also binary tree because it is having even a single node. It has no children, right? Then one child condition. You can have 1 child, or you can have 2 child. Again. And now tell me, is this a binary tree? The one which is constructed?
Yes, ma'am.
Yeah, this is also a binary tree. It is not necessarily always it has to be a perfect binary tree. Maybe if you're talking about some perfect tree, like it has to be all the levels should be same, all the leaf nodes should be like all the leaf nodes should be in the same level. That is okay. So this is a binary tree. So when I give you some data to insert, for example, and so on, just example. So you'll be having a root node. The first node you'll be having a root node. Then you'll be just, because maximum only 2 children, so you'll be occupying. So in this fashion, you'll be inserting. Right. So to add to this binary tree, we'll be learning about binary search tree. So just extension. So you know what is a tree, you know what is a binary tree, how many children it can have possibility. Now just extension. So there is something called binary search tree. So here there is a two properties that you have to maintain. You can see the diagram given here. Let us say you have a node value. You can see the left representation and the right representation. So whenever we insert a value in this particular tree, we are going to make sure the value lists, for example, let us say this node value, say k, for example, some k is the name of this particular node. So the value you are going to insert, if this value is less than the node value k, then it has to be placed towards your left subtree. You have to concentrate. If the value you are going to insert is greater than your node value that you are checking, so here it is k. So if the all values greater than k will be placed on your right hand side. Now you can look at this particular diagram. Say root node value is 25. If the next value say 20, you can say 20, 10, 22, all these values you just check. All the values will be always towards the left hand side value will be less than 25. Similarly, you just check the values that are present here in the right subtree. So all the values greater than 25 will be available in the right subtree. So this is not restricted only to the root node. So this is applicable in all the levels, starting from, you can at least see from the bottom to top there. You can see every level this property is satisfied. If you take 5, in this subtree again, 1 less than 5 is placed in the left side, 8 greater than 5 is placed in the right. Similar to the top level, you can see this subtree from 10, 5, 12, 1, 8, 15. 5, 1, 8, you can see here, right? 5 less than 10. Similarly, 12 and 15 are greater than 10 will be placed on right. So this is the way we will be learning about how to insert element or delete element or so on. But why you need this? See, you know, tree, okay, just a hierarchical representation, okay. You know, binary tree, okay, confined to maximum 2 child, that is also okay. Then why you have to learn all these things? What is the necessity for learning, representing a data in the format of binary search? There should be some purpose, right, for learning any concept. Maybe I will give an example. Just I'm asking you to just construct, then I will explain you the advantage of this. Just construct a binary search tree with input elements, say 10, 12. Enough. So what is the first node you will insert? What is your root node value?
10.
Okay. Where you have to insert this 12? Towards the left or towards the right? I told the binary search tree property, values less than the node you are comparing, right? So always you have to start with the node value. So where you have to place? Yeah, 12 greater than 10. So we are placing it in the right hand side. What about 1? So again, don't check from 12. Always you have to start your checking from the root node. Okay, so 1 less than 10 or greater than 10? Less than 10. So it has to be placed towards the left. The next element, yeah, you can check and you can tell me the answer where I have to place this 3. Start from the root, start comparing. Is 3 is less than 10, right? So then you have to
Right side of 1. Right side of 1.
Yeah. So 3 is less than 10. Always we have to start comparing from root. So you are moving towards the left subtree. Again, compare with 1. So 3 is greater than 1. So 3 has to be inserted in the right of 1. Right. In the same fashion, we have to insert the other elements. For example, if you are taking 5, 5 is less than 10. So you are going towards the left. Again, 5 is greater than 1. So you are moving towards the right. Now compare with 3. 5 is greater than 3. So I have to insert 5 towards the right of 3. Same 4. 4 is less than 10. Come towards the left. 4 is greater than 1. But 4 is again greater than 3. When you compare with 5, 4 is less than 5. So it has to come towards the left of 5. Similarly, what is the next mark? 7 and 8. You can just tell me where I have to insert 7 and 8.
7 to the right of 5
Yes.
and
8.
8 to the right of 7.
Okay. Maybe let us say I have not given this set. Let us say you have 14, 18, 13, and so on. Then 14 will be towards the right of 12, 18 again, 13
Left
greater
side.
than 12. Am I right? So 13 start from the root, you are comparing and you are going to place the correct position. Less than 14. Okay. So now I am giving, now this is the tree. Okay. I am giving you a question. Find minimum element. You have already done this, like finding the minimum element from a given array, finding the maximum element from a given array, and so on. We have discussed the time taken also. What is the time we have discussed? I remember I have discussed, but if not, just recollect, like for how to find a minimum element or maximum. These are some of the general things. So how will you find a minimum element in this BST, in this binary search tree? Now you have a tree. I want you to find the minimum element in this binary search tree. I'm not asking any program or algorithm. I'm asking the idea behind this, how we can find the minimum element.
Starting from the root node and going to the leftmost child, descendant.
That's all. Yeah, problem is simple. Starting from the root node, moving towards the left will always give me the minimum value, right? So if I ask you to find the maximum element in this binary search tree,
Rightmost to left.
yeah. So you are constructing the tree in such a way, the elements are inserted in such a way, the maximum, if you, so now here, what is the advantage? Okay, towards the right, if you traversed, yeah, from 10, go to the right, 12, go to the right, 14, go to the right, 18, again, there is no more node. So here that is null, right? There is no node here. It is null. So you will stop, you will be returning 18 as the maximum, right? If I ask you to find the minimum element, you will, starting from the root node, you go towards the left. Is there any left available? No, it is null. No more node. So you will stop, you will return this value. So you'll be returning the minimum value as 1. Okay, so what is the benefit in this? You have already studied array, you have studied linked list. So what is the difference you are going to recognize in this with respect to time?
We are reducing the search area by half every time.
Okay, so you are, we cannot tell half, maybe I will come to that part later. Half I will come later. You are reducing the search space, that is right. So if you are going to use an array, maybe you will be doing a linear scan and then you will be finding the maximum element or minimum element. Or if you are going to tell, maybe I will sort the array and then I will apply the algorithm to find the minimum or maximum element. But again, to sorting, it will take time, right? You cannot ignore that. So again, you have to spend some time to sort the data. Maybe after sorting, you can tell me, maybe the given elements after sorted order, the first element will be the minimum element, the last element will be the maximum element. You can get the minimum and maximum in O of 1. But sorting time, you have to include. So that again, it will be something in n log n. So here, the advantage is you are reducing the search space. I accept. So you are not going to trace everything, right? So if it is a minimum element, it is sufficient if I'm going to search only in my left subtree. Or if it is a maximum element, it is sufficient to search only in the right subtree. So I accept. So what is the worst case time taken? Or even if, Isma, what is the worst case time taken?
O of n.
O of n. Any other answers? Apart from this? So these questions are just to think. It is not that you have to always give a correct answer, right? What is worst case? The maximum time that is going to take. That's what we discussed in the basic. What is best case, average case, and worst case time complexity. So the worst case is O of n. Okay. Any other answers? Just now we discussed linear search. It is going to give O of n. But now this binary search tree, after constructing this is also giving O of n. Why? Worst case. I'm not talking about best case. I'm just talking the worst maximum time taken is O of n. Why? Or any other answers? Anyone having any other answers? You can tell me the answer. Okay, type in chat. Just let me check the chat also. Okay, faster search for insertion and deletion. Yes, you are right. Searching is faster. Maybe this is not confined to finding the minimum or maximum element. Even the question is search element, right? If I want to search 5, okay, the question is search 5. So if you are going to have a binary search tree, again, the search space is reduced. I don't want to search in my right subtree at all, because when you are giving a key value to be searched 5, from the root node, it is very clear the 5 is less than 10. So you will be focusing your concentration towards the left. Again, you will compare here. Again, 5 is greater than 1. So whether you have element here or not, you are not going to concentrate this area. You will be concentrating again on the right subtree. Again, the next element 3. So even if you have any subtree here, you will ignore. So again, the search space is reduced. So it's not restricted only to finding minimum or maximum element, to insert a record, to delete a particular node, or to search a particular node. And these some of the exceptional cases, minimum, maximum, and so many things. So you're telling all these things, but why it is n? I can do this in n means, then what is the use of learning this BST? Why it is coming as n? The worst case. I'm not telling it is n for always. The worst case, it will be n. Why? Maybe.
Ma'am, it could be like a BST could be in such a way that it's only all the right subtrees or it's only all the left subtrees. So
Yes.
in that case.
Yes, ma, correct. So there is a scenario, there can be a scenario where if I'm asking you to insert element, this is the given record. This is a record. So when you construct a binary search tree for this data set, so you'll be getting 1, then 2 greater than 1, so 3, 4, 5, 7, 11, 13. So this is also binary search tree. Am I right? Everyone agree? This is also binary search tree. Your property is satisfying, right? So it is having maximum, it can have only 2 children, that is okay. The value, what is the node value? The value towards the left should be less than the node you are comparing, and again the right hand side value should be greater. This is satisfying. So this is the binary search tree. Am I right? But how it looks like? It is a skewed one. Okay. Even if the element is like this, for example, maybe I'm giving data like this, 5, 4, 3, 2, 1. So this is the elements to be inserted. Now you can get a tree 5, 4 less than 5. So we'll be inserting towards the left. 3 again less than 5, less than 4. 2 less than 5, less than 4, less than 3. And so this is also a binary search tree only. So this generally we call it as a left skewed, right skewed binary search trees. So if this is your binary search tree, now if I'm asking you to search element, okay, maximum, let us say same question. Now I'm asking you to search maximum element in this. Now student who answered me, it reduces the search space, but this is the worst case scenario. Again, I'm telling this is not for all the cases. Best case, that is fine. The maximum time I'm talking. This is the worst case scenario. Now what is the time taken? If I want to find the maximum element, or this side, if I want to find the minimum element, what is the time taken?
For minimum, ma'am, it's O of 1. And
This
for
one,
maximum, O of n.
For minimum?
O of 1.
Oh, what?
1, ma'am, constant time.
How, ma?
Ma'am, because there is nothing in the left.
1 minute. You are talking for this tree, right?
Yes, ma'am.
Okay. Pertaining to this tree, maybe. Okay, yeah. For this tree, in general, you are telling for finding the maximum element, you have to traverse till the end. So it is O of n. I thought you are telling, okay. What about for this tree? What will be the time taken for finding the minimum element? For this tree, what is the time taken for finding the minimum element? This is fine. For maximum element, you have to traverse from the root towards the right. So you have to check all the end nodes available. So like it will be O of n. Okay. What is the time taken for this tree? 5, 4, 3, 2, 1. What is the time taken to find the minimum element?
O of n.
O of
N.
Yeah, same. That's all. So these are some of the worst case scenarios. Okay. If the tree is not a skewed one. So if the tree is not a skewed one, if it is a binary search tree, it's a normally it is like this. Now you are trying to find the maximum or minimum, or you are going to find the, so now what will be the average time taken? You can tell, okay, it is log n. So since you are not going to check both the halves recursively, you will be searching, you're reducing your search space in only one half. In general, maybe you can tell log n, but the worst case will be always n. So how we can overcome these kinds of issues, right? So this can be overcome by balancing. So this is a normal BST tree, but we have, this is a normal BST tree, but the problem is this is a not balanced, right? So it is not always balanced. So this is, even this we consider as BST, this we consider as BST. So we have some ways to balance this. So we can balance. So this balanced binary search tree. So that can be like we have some Avl trees, red black trees. Okay, so these are some of the trees that we'll be using for balancing it. So maybe before going to this one by one, I will make a pass here. I will just check the. Anyone having difficulty in understanding the binary search tree insertion? How we inserted the elements? Is it clear for everyone how to insert element in a binary search tree? Because before moving to the other part, like balancing, again, we will compare the time taken. So what is the time taken? So before moving to that part, anyone having difficulty in understanding the BST insertion part? So before moving next tree, maybe I will explain the deletion also, then we can move for the balancing part. So these things we discussed. Just I'm moving this slides. So yeah, these are the operations, insertion or search or deletion we can do on the binary search tree. So this is the algorithm we use, right? So to insert a node, what we will check? We check that the root is null. If it is null, it is an empty tree. You are going to create the first node as a root node. Then what you will do? You will compare the data with the node data value. So if the data is greater than the node data, then you have to move towards the right subtree. Otherwise, you have to move towards your left subtree. So after getting the correct position, you will insert your data. So this is with respect to insertion. Just now we inserted element. Similarly for searching also. You will compare whether the element to be searched is equal to the root data. If it is equal, the problem is over. You will be returning the root value. Otherwise, you can confine your search in either left side or your right side. That is left subtree or the right subtree. Can't be based on the condition. So if the data to be searched is greater than the node data, then it is enough to go to the right subtree and do your search. That's all. Because the recursive way we will write the algorithm. Or it is sufficient to the left subtree if the data to be searched is less than your node data. So these are the general ways searching for insertion. So coming to the deletion part. So that will be slightly maybe a same tree I can show and you can just identify. Okay. You want to delete a record. Okay. Maybe I want you to delete node. I want you to delete a node 13. Right? Is it difficult or easy to delete 13? Looking at the tree. Start from the root node. First, for deleting, first you have to search, right? So before deleting, you have to search and you have to identify the node. So you have only the root node address. Starting from the root node, you will be searching this particular node 13. After identifying the node, can you delete this now?
Yes, ma'am.
Because there is no, it's a very simple case. You don't have any children, so you need not worry because it is a leaf node. So you have identified this node from the root, you trace and search the location, and this is simply, it is a leaf node. So you can just, after identifying this particular location, you can call the free function, free method, and you can free the memory address occupied by this node. So the problem is over. Suppose I'm asking you to delete, instead of 13, I'm asking you to delete maybe, just a minute. I'm asking you to delete node 1. Okay, instead of 13, I'm asking you to delete node 1. Now look at the diagram and tell me how will you do this deletion.
Ma'am, we have to delete the link between 1 and 3 first.
Yes, you have to give the link to the.
We have
You're
to
right. You're
delete the link first, ma'am. Between 1 and 3.
See, to delete 1, you have the root address pointers. You have to trace this 1. So if you delete this 1, what you have to do, you have to just link the. It's a single child condition, right? So if it is a leaf node, the problem is simple. You will call the free function. There is nothing to worry. This is a condition where this node is having one child. Okay, it is a single child condition. So in this scenario, you can link this node's parent and children. This link you can make. And then you can call the free function to delete this. Is this what you are telling, right?
Yes, ma'am.
Okay. So it is a single child condition where you can link the node's parent with its children, single children. Whether so here it is a right child. So, or if I'm having a scenario where I have only one left child, so that is the same thing. So this is single child condition. Now I will show this. Now you just explain. So we have a, for deletion again, we cannot just like that, we cannot delete the data from a tree. So we have to ensure what condition we are in or in which case we are. So it is a leaf node case, then no issue, right? Or if you are having a one child, what has to be done? Or if it a node with two children, that node I'm asking you to delete, then how we have to delete it. Okay, so this is what we have done. If I want to delete a leaf node, the problem is simple. We will be just searching the node to be deleted. We will call the free function. So if it is a leaf, the problem is over. You just remove the node and the tree will be as it is. Suppose the node to be deleted, it is a single child. In that scenario, so here let us say they have to want to delete 9, node number 9. So after searching 9, we can check whether we have one child or two child, that we can check. So it is a one child scenario. So automatically we can create a link between this node's parent and the child. So you can, this is the updated tree. So 8 will be connected to 12 and just will be using free function. We can just remove this memory occupied by this node with the value 9. The third scenario is slightly complicated, not complicated, easy only, but lightly maybe confusing. The question is, now you want to delete a node, but that node is already having 2 children. So it is not a 0 children case or not a single child case, a node with a 2 child case. So this is a case. So this is a node 8 that we want to delete, but this node is having 2 children, right? So in this scenario, we have to make sure we have to remove this node. At the same time, the binary search tree property should not be violated. So we cannot just like that, we cannot link with 3 or 9. So we have to make sure the BST property is not violated. So for this case, either you can identify the maximum element from your left subtree or a minimum element from the right subtree. Anything, any one thing is sufficient. So it's not that you have to always do the same procedure. Either go for maximum element from the right from the left subtree or minimum element from the right subtree. So here in this case, finding the maximum in the left subtree. So the 5 is the maximum element in this left subtree, 3, 1, 5, 4. So this is a left subtree, the maximum value is 5. So after identifying the maximum value, you can swap that particular value with the node to be deleted. So 5 will be moving to the 8 place, and 8 will be moved to this 5 place. After moving that, then you can check whether it follows case 0 or case 1. So now 8 will be coming under case 1 category, single child condition. So if single child condition, just link the parent with the child. So 3 will be connected to 4. So that's what happened here. Is it clear? Is it clear, or shall I repeat?
Please repeat, ma'am.
Yes, ma'am. For a node in a binary search case, especially in a BST, if you want to delete a node, if that node is having 2 children, then you have to identify maximum element from the left subtree or minimum element from the right subtree. In this case, any one thing. It is not that you have to take only either you can go for max if you want either maximum or minimum element. So maximum element from this left subtree, if I'm going to take 5 is the maximum element in this left. Swap this data with the node to be deleted. So here I want to delete 8. So 8 is having 2 children. So I'm going to the left subtree and I'm checking what is the maximum element in this left subtree. So the maximum element in this left subtree is 5. So I have to swap this 5 and 8. So 5 will be coming towards the top and 8 will be coming here. Now you have to check this at this position. 8 is going to be, to delete this 8, again you have to check whether it is falling under case 0 or case 1 or case 2. If it is case 0, leaf node, again you can just remove it as it is, free function you will call. If it is case 1, this comes under case 1, single child condition. So you will be linking the node with its parent. So 3 will be connected to 4. That's what happened here. 3 is connected to 4. After swapping, I'm talking. Okay, so now 8 is removed. So actually this is not 5. 5 is moved to 8 position and 8 is moved to the 5 position. 8 is deleted since it is having single child scenario. Again, if it is having 2 case, like again 2 child scenario, then the same algorithm has to be applied recursively until you delete the respective element. Is it clear now? Maybe I will just explain. So we have identified the node to be deleted. So if it is 2 child case only, we are doing this, finding the largest node in the left or finding the smallest. It is not mandatory. You have to always swap with the largest element from the left subtree. Even if you take the smallest from the right subtree, that is also correct. So any one thing, either this or that, any one you have to follow, swap the node, then check the deleting node case, which case it is coming. If it is coming case and case 2, then problem is over. Otherwise, if it is again having 2 child scenario, then repeat this process. So this is with respect to the BST deletion part. Is it clear now? Yes, sir. No, ma.
Yes, ma'am.
Yes.
Okay. Okay. I have 2 things to explain after this. Maybe I will explain the why we are going for Avl Tree. Maybe that I will explain what is the benefit you have to learn this balancing. Then I will explain you the coding part. So how to write a code to implement this scenario. I will explain the coding part as well. So maybe Avl Tree I will complete, then I will share the coding part also. So this is regarding to BST. So just now we discussed the drawback of binary search tree. So that's what we have seen here. So this is inserting or deleting, searching, that is fine. So but the maximum time taken will be n if the tree is a skewed one. So this is the one drawback we discussed, because this is not a balanced one. So this is worst case is possible if the tree is not a balanced one. So to make it balanced, we have many other variations like Avl trees or red black tree. So we'll be constructing a binary tree that follows this balance. It should be balanced. In such a way only we'll be constructing the Avl trees. So if it is balanced, then automatically you can strongly tell me, okay, let me show that, then you can tell the time complexity associated with that. Okay. Okay, how will you tell a tree is balanced? Based on what you can tell a tree is balanced? Height of? Okay. Okay, this tree I'm telling this is not balanced. And how and what factor determines me telling this is not a balanced one? Looking at the diagram, how will you judge whether it is balanced or not? What is the key factor in determining this particular tree is a balanced tree or it is not a balanced tree? So what is the factor that helps you to determine?
The height of the tree must be.
Yes, height of the tree. So whenever you look at the tree, when you calculate the height, you can tell here you can compare the height of your left subtree and right subtree, right? Maybe if the tree is looking like this. Sorry, it's not a binary search tree. Just I'm writing a normal tree. Don't get confused. Just a normal binary tree, for example. So the height of the left and right helps you to determine the tree is a balanced one or not. Right? If there is no node in the left, you have all the nodes in the right. So that you will be having the tree focused towards a skewed one. It will be a skewed one. So in this Avl tree, so this strategy is followed to determine. So every time, how will you make sure it is balanced or not? So something related to the height of your left and right. So it is a self-balanced binary search tree. So a binary search tree is said to be balanced. So when it is said to be balanced, that's what I'm asking. So how will you tell it is balanced or not? So you have to check the difference of height of your left and right subtree. So for every node in the tree, so this is the maximum difference in height allowed. So if I calculate the height of left subtree and the height of right subtree, the difference between the height, if it is belonging to the range -1 or 0 or +1, then we can make sure, okay, this is a balanced one. If we are going to get a value other than this, maybe I can get a difference of 2 or 3 or 4 or -2 or -3, -4, etc. So that indicate it is not a balanced tree, it is a unbalanced one. So these are the ways we can determine whether the tree is balanced or not, but finding the difference in height of your left and right. So we can maintain something called balance factor to manipulate. So just a simple formula, just height of left minus height of right. That's all. It's not a very big, difficult formula, just a simple thing. So to make sure it is every node, if you are checking the what is the balance factor, just to manipulate what is the height of left subtree, what is the height of right subtree, find the difference. So that difference will give you what is the balance factor of that particular. So if that balance factor of each and every node, if it is going to be in this range, then the tree is balanced. So no need to worry. If it is not in this range, then we have to do some rotations to make it balanced. So that's what we'll be learning in this particular tree called Avl Tree. So Avl Tree is also a binary search tree. So that's what Avl Tree is not something new. If you know binary search tree, then Avl Tree is the same thing. But only thing is, we have to make sure the tree is balanced. So to make it balanced, we will be doing some manipulation. That's all. So let us take this example. I'm not going to again tell the same thing because you know how to calculate height. You know how to find the balance factor. Now you can look at this diagram and tell me what is this 0, 1, 0 and all given above this data, how it is manipulated. So it is the 1, 0 and all, it's a balance factor. That is okay. But how it is calculated? You can just look at the diagram and identify how these values are calculated. So the balance factor is given as 0 for the node value 12. Why? Balance factor is height of left subtree minus height of right subtree. So is there any height associated with the node 12 towards the left and right? Is there any left subtree and right subtree available?
No, ma'am.
So simple, 0 minus 0, 0. That's all. Same thing for all the leaf nodes that you are encountering, 28, 38, 48. That's all. Coming to one level above, the upper level, node 10. So this node balance factor, how we are going to calculate? Height of left minus height of right. There is no left subtree available. So it is 0 minus 1 for the right subtree. So 0 minus 1 minus 1. In the same way, you have to calculate for the rest. So for example, for node 20, what is the height? Sorry, what is the balance factor for this particular node? Height of left minus height of right. Now, what is the height of left subtree for node 20? Just tell me the height of left subtree. Yes, ma'am?
2.
2. Yes. So the height is 2, right? What about the right subtree height?
It's 1.
1. So 2 minus 1. So in that way, the balance factor is calculated. So the same fashion, it is calculated for all the nodes in this tree. Now you can see in this particular tree, the balance factors, you can see the value 0, allowed, 1, allowed, minus 1, allowed. So this is a balanced binary search tree. So here it has to binary search tree properties also satisfied. You can check that all the values towards the left will be less than the node value, all the values towards the right will be greater than the node value. For each and every level, recursively, just to check it all the subtree in each and every level, this property is satisfied. So this is a binary search tree. One more additional thing, is it balanced or not? Here it is balanced. So we have calculated the balance factor. It is not outside the range of 0, 1 and minus 1. So it is a balanced binary search tree. So if this is not, so that's what every Avl tree is a binary search tree, but every binary search tree need not be Avl tree. So if it is not balanced, then what we have to do? So if it is not balanced, like if you are getting the difference as -2 or +2, so on. So if it is not balanced, then there are some rotations to make the tree balanced. So that maybe I will explain. Just we have two types of rotation. One is single rotation, another one is double rotation. Again, in single, either are we going to do a left rotation or right rotation? If it is a double rotation, we can do left right or right left. These are some of the way to do the rotation to make the unbalanced situation to a balanced one. That's all. So maybe in this case, you can see very simple data. Only three nodes, 1, 2, 3. So when you construct a binary search tree, you can see. So one you will be in, maybe if it is confusing, I will explain separately. So you just insert in some cell Avl tree. That's all. We are going to check the balance factor. That's all. So normal binary search tree, will you do the same thing? So one will be your root node. Then one more thing you have to do. You have to always calculate the balance factor for every node. That is the additional thing you will be using for Avl tree construction. That's all. So what is the balance factor for this particular node? Am I right? Height of left subtree minus height of right subtree. So it is 0. Next element. How will you insert the next element? Where it will come?
Right side.
The same BST. See, when you want to do same, BST has to be followed. Nothing special. Same BST along with balance factor. Right side. Now calculate the balance factor. This is 0. This is 1. Sorry, 0 minus 1 minus 1. So what is the allowed range? The allowed range, if it is in this range, it is allowed. If it is going outside this range, then we have to learn about rotations. Now it is balanced. No, nothing to worry. The next node, you want to insert 3. Now if you check the balance factor, what is the balance factor for this node?
One.
No.
-2.
Yes, because we are calculating the height of left. The height of left is 0. minus height of right, it is 2. So it is 0 minus 2 minus 2. Now this value is not in the given region. So it is unbalanced. So what is the objective of this Avl tree? It is a self-balancing binary search tree. So we have to make it balanced. To make it balanced, we have to know this rotation. Okay. So that's what given here. So to make it balanced, we have to follow the rotation. So in this rotation only, you are learning this first rotation. It is a left-left rotation. If the given data, you are getting balance factor affected at this level. So now after performing left-left rotation, so this will be a final out. So single left, again double left. So 2 will be the root and 1 will be the left child and 3 will be the right child. So just a single left-left rotation. So if I do left-left rotation, the final rotated value will be 2 will be the root, 1 will be a left child, 3 will be the right child. Now calculate the balance factor. 0, 0, 1 minus 1, 0. Now it is balanced. Just in the same way, maybe if the data to be inserted is this 7, 6, 5, for example. So 7 will be the root. If the balance factor 0. After you insert, 6 less than 7, so it has to be inserted towards the left. The balance factor is 0. Now it will be 1 minus 0, 1. Now when you insert 5, 0, 1 minus 0, 1, 2 minus 0, plus 2. So again, the balance is getting, it is not balanced when you get plus 2. So again, you have to call the rotation. So this is right rotation. So you after doing the right rotation, 6 will become the root, 5 will be the left, and 7 will be the right. Now you calculate the balance factor 1 minus 1. Now we have made it balanced. Is it clear, ma? Double left and double right rotations to make the node tree balanced one. If this is clear, we can go for double rotation.
Yes, thank you.
The next strategy, the next rotation is we have double rotation. Either LR, left right, or right left. That's all. Suppose a node is given like this, maybe 7, 11, 8. 7 greater than 8, but less than 11. So here also the balance factor 1 minus 0, 0 minus 2, minus 2. So in this case, first what you have to do? First you have to make a single right rotation to make it balanced. So this either zigzag category, either a node looking like this. If here if the balance factor is affected, okay, for this or this scenario. So first do a right and then do a left. So if I do a right, what will happen? 7 will be here, 8 will be coming here. After this, do a left rotation. So the final outcome will be 8, 7, 11. Now you check the balance factor. It will be balanced. So this is called RL rotation. First one single right. In the previous case, we have completed both left rotation, both right rotation. But in this scenario, like zigzag, where you have to perform a single right followed by a single left. That is a right-left rotation. Maybe a scenario like this, for example. 31. 46. Again, the balance factor 0, minus 1, minus 1. This one, 2 minus 0. Okay. So here, again, you have to make a single left. Then 31 will be here, 26, 24, then right. So you'll be getting 26 as a root, 24 will be a left child, 31 will be a right child. So now it is balanced. So these are some of the rotation types. This is the left-right rotation. So coming to the time complexity. Okay, you do all these some rotations and all, and you are making sure your tree is always balanced. So what is the purpose of learning this? So whatever you have doing these rotations or making the node to balance. So what is the purpose? So why I have to make the tree as a balanced one? Why not? It can be a normal BST tree. It can be a maximum worst case n we discussed. If it is a skewed tree, it is taking O of n. So in Avl tree, it is a self-balancing binary search tree. With the help of this particular balance factor, we can find whether it is balanced or not. Then we are going to use these kinds of rotations to make it balanced. So what is the aim of learning this? So after this, you are getting maybe the element inserted as this, for example, you are going to do some balance and you are going to get a balance return, right? I'm just writing some dummy value. You are getting a node 1. After balancing, you are making sure the tree is not a unbalanced one. For example, I'm just writing like this. Something like this. Okay. So what is the advantage of this balancing? Now, what will be the worst case time taken? Now the question, same question. You are finding minimum element or a maximum element, or you are finding, let us do some search operation. Why you are worrying about it? Just simple search. I want to search whether the given tree is available in this node. So what will be the time take? If this is a Avl tree.
Log n, ma'am.
Log in. Any other answers? Any other answers? One answer it is log in. Okay. Any other answers? No. What is the time taken to perform a search operation in this particular tree, Avl tree? Okay, no answers. Login is correct. Login is correct. So why login? Why not n? In the previous binary search tree, we discussed the time taken in worst case is n, right? But here it is not n, it is login. Why?
Ma'am, because this becomes a similar search like binary search. We are dividing the tree every time we make a comparison.
Yeah. See here, yeah. So if it is a normal binary search tree, yes, as you said, for the worst case scenario, if the tree is a skewed one, left skewed or right skewed, you have to search element, or you want to insert elements. So this worst case n is possible because you have to trace or you have to move towards the same direction, right? So it is the maximum time taken will be n. But here, whenever you are constructing, you are balancing it. So whatever rotations, whether it is a single left or right or LR or whatever it is. So what is the purpose of doing this rotation? To make the unbalanced situation to a balanced one. That is the objective. So final outcome by calculating this balance factor, finally, you are making sure the tree is a balanced one. By checking the height of your left and right, you have calculated this balance factor and doing all these rotations, and the tree is the final outcome or final constructed tree will be always a balanced one. So once the tree is balanced, so the height will not be a one, will be like a skewed one. So it is not possible to get a skewed nature. So at this situation, if you are going to search a data or if you are going to insert a data, okay, whatever it is, or you're finding the minimum, whatever maximum element, whatever the scenario, so you will be having efficient search space, right? It is not that you have to search all the nodes. So it should be log n, not n. Is it clear why the time taken is log n? Others, like if you're not able to understand why this is log n, then you can let me know, I will explain. The previous example for normal BST, the worst case I told n, but here I am telling log n. So if anyone not able to understand the time taken, why it is log n for this case, then you let me know.
Ma'am, explain one more time.
Yes, ma'am. See, when you are getting n, see, normally tree is in a hierarchical nature. You can reduce the search space. It is confined to one half. That's what we are discussing. The same example that we discussed in normal binary search tree, right? So normal binary search tree, whenever we constructed to find a minimum element or maximum element, it is sufficient. If I search towards my right, I will get the maximum, or if I search towards my left, I will get the minimum. So my search space, this is a general thing. So what is the drawback in this? If the tree is skewed scenario like this, then the drawback is you are not able to reduce the search space. You have to go through all the you have to visit all the nodes to obtain the maximum or minimum or search, whatever it is. So the worst case, you are visiting all the nodes. So let us say you have n elements. To find the particular element, the worst case time taken will be n also, if the tree is a skewed one. So to reduce the time taken, when we are going here, the problem is it is not balanced. Suppose if you are going to make this balanced, you are this particular Avl tree concepts. These are some of the methods, red black tree, that that we can just it's another way. Using colors, we can make it balanced. That's another methodology. So using Avl tree, what we discussed now was using this balance factor concept. We are checking whether the height is the tree is every node. So for every node level, it's not the entry tree. Every node we are checking it is balanced or not. How we are checking? By checking the height of the left subtree and height of the right subtree difference we are calculating. And if it is in the allowed range of -1, 0, and +1, nothing to do. You can just continue your problem. Otherwise, if it is outside this range, we are doing this rotations and converting this unbalanced one to a balanced one. So whenever the tree is balanced, you won't get this kind of skewed nature, right? If you're going to, because whenever you encounter at node 7 itself, you will identify, okay, the height is, the balance factor is say -2. So you'll make it balanced. So you're making sure the height in the left and right is not having a greater difference. So when it is balanced, you will be getting not, get this skewed nature trees. So you'll be getting in a balanced way. So now if it is somewhat balanced, then if I want to search element or if I want to insert a record, whatever operations you are doing here, you will be having an efficient reduce of search space. Am I right?
Yes, ma'am.
So time taken will not be n in the worst case for this scenario after balancing. So time taken, you can strongly tell, okay, it will be log n. Since we have balanced it, so time taken can't be n, it will be only log n. Is it clear, ma'am?
Yes, ma'am.
Now maybe I think I can show some visualization. That is fine. Maybe if you're using your laptop, so you can just open this parallelly. You have I don't know, maybe in the previous session Sir have told this, or maybe Sir has suggested some other platform. Have anyone heard this one, ma? Visualgo.com? Have you used this? Maybe in Ram Prasad sir class, I am not sure. Have you, whether you have used this or not? Just I want to. Visualgo you have used?
No, ma'am.
Okay, maybe I'll type in the chat. Just, or if you can see the screen, you can just note it down. Visualgo.com. Just open your Google. Just type visualgo.com. The chat also maybe I will type. Just in Google, if you type Visualgo itself, automatically just type in Google Visualgo. That's all. Automatically, you will get the first link. Just click on the first link. You will be getting this page. Will show from the beginning. Just open your Google and type Visualgo. Just type visual code. The first link, visualizing data structures and algorithms. The first link. We can look the screen. Just it's like maybe even if you are not able to understand, this is not with respect to tree concept. This is with respect to the entire data structure. You have for linked list, simple sorting. I said you have some animation to understand how it happens, along with the algorithm that appears parallel. So if you're not able to understand how this algorithm works, sorting algorithm, or if you want to know how the single linked list work or doubly linked list work, or if you want to know this tree concept, how the tree is constructed, how the elements are inserted, so you can just explore that. If it is linked list, you can go to the linked list part and you can explore how the nodes are connected. Okay. Maybe today I thought of explaining tree. If anyone wants me to, maybe I will just show how to use this. Then I will go to the tree part. See, if you want to explore, how the nodes are connected. So what is the algorithm behind that? Just open the linked list, for example. Okay. Again, you can choose here what you are going to do. You have to see. You can now see the options here: linked list, stack, queue, doubly linked list. So you have the options. So whichever you want to explore, you can check. So first time, if you want to know, you just create. Just click that. I think the screen is visible. Am I right? Because I have shared the screen. Yeah, you are able to view the operations, right? Create, empty, and all.
Yes, ma'am.
Okay. So like if you want to start, as you want to just have a start, just create empty. If you want to know how the linked list is created, simple. Just insert. Maybe for the first time, I don't want any random. I want to insert by myself. Then you can specify the position. You are going to insert at the beginning, or you are going to insert at the end, or you are going to insert at a specific location. So all these variants that you have studied, you can just visualize. So for example, the first time I'm going to insert, let us say I want to insert the node or some, you can use the same value, no issue. Or if you want, you can just define your own value. But with the maximum ranges, it's only up to 99. If you type 100, it will not accept. So maximum till 99, you can give some numbers. Okay. You can parallelly, whenever a node is created, along with the visualization, you can see the code here. So this is not a code with respect to C language or C++ language or Java, nothing. So this is a pseudo code, like what is happening here, along with the visualization. So what is, we have created a vertex, that is a node. Okay, and then this is your head or tail. Both the nodes point a single node. So single node creation. Similarly, if you want to insert a node at the beginning, so head beginning, the value say 1, let it be 1. So now this one var has to be linked. So the 1 has to, now you can see here. So the 1 has to be linked before this 85. So this is something equivalent to insertion at the beginning of the linked list. Now you can check the code. So we have created a vertex. The vertex value say 1 we have created. Vertex dot next is equal to head. So what we are doing here, we are just giving the vertex address, next value, address value is equal to head. So now the link is made. Now what is your new head? Is it 85 or 1, the current head?
85.
Then you have to update it. So you can check the code parallelly. So 1 is your current head, means you have, because the algorithm will not know if you are not specific. According to the existing one, 85 is the head. You have to update your head is the newly, because this is insertion at the beginning. So the node, after inserting at the beginning of the existing node, the head has to be, pointer has to be updated to the node 1, not 85. So you can see the third line of the code here, which is given in the box at the bottom. Head is equal to vertex. So the newly inserted node, that is VTX, so that will, the head also will point to the same. So in this way, for self-learning purpose, so if you want to visualize and see what is happening, how this insertion is happening, what is the code, so how the code is written, so this will be very useful for the beginning level. Okay, you need not directly go and see some C programs to avoid the confusion. First, understand the basic outline, then you can start your coding part. So same thing, if I want to insert, maybe insert at the end. Okay, insert at the end. Okay, let the same value 80. So 80 has to come after 85 because this is insertion at the end of a single linked list. Okay. Now see the code and tell me what is happening. This is very easy to visualize, right? To insert a node at the end of a linked list, we have two elements, 1 and 85, and 80 is just going to be inserted at after 85. But look at the code. Here we are maintaining a tail pointer. So in one line, tail next equal to vertex, you can tell tail equal to vertex. Suppose you are not going to maintain a tail pointer, you do have only head pointer, then you have to go with the normal procedure that we follow. Get the head node address, assign some temporary pointer, traverse it till the last node, then do this insertion. Okay, you have to iterate till the last node, then you have to do the insertion if the tail pointer is not maintained. The same fashion you can explore for the rest, maybe for a removal. Similar, maybe insertion after a given position, or removing a node at the beginning, removing a node at the end, or removing a node in a given position. All this you can just explore and you can visualize how it is happening. If I'm giving removing at the head, the first node has to be removed. Simple, temp equal to head. If empty linked list, you cannot delete. That is a normal scenario. Otherwise, get a temporary pointer, store the head value, move head to the next element. So instead of 1, head has to point to the head next. 85, then delete temp. That's all. The same thing you can do for a stack. You can you can explore for stack how the code is, how the logic behind this. You can try for queue, you can try for doubly linked list, and so on. Okay. So please make a note of this. So coming to the binary search tree part. Similarly, if you want to explore data structure, other concepts like, or I want to know sorting itself, you can choose sort, you can choose an algorithm, bubble sort algorithm, you can see how it is actually working. You can see with the animation or heap concepts and so on. So now we are discussing binary search tree. So I will open that. I request everyone to make a note of this link. Okay. Great. See, if you want to know how the binary search tree elements are constructed or how to insert Avl, just go to BST tab inside Visual Go, and you can just insert the elements. And the important one thing I forgot to tell, forgot to tell one important thing, which is tree traversal. Okay, we will cover that. So this part you can just visualize, maybe inserting. Maybe I will explain along with this. Maybe we'll insert some elements. Okay. And I will tell how to do the tree traversal. You can just parallelly explore. So 1 is inserted, 2 greater than 1. So we are inserting binary search tree. 3 greater than 2, 12, 1 greater than 1, 2, 3, 34, 56. So we have given a skewed tree. Okay. So skewed binary search tree we have done. Maybe I can insert some more elements. Okay, maybe to avoid confusion, I will create a normal tree. Like, don't go for skewed in the beginning. Without a skewed factor, I will put 23. Okay. Yes, ma'am. I look at it. Okay. I hope everyone is clear with how the tree is constructed. No doubts in this, right? How the binary search tree is constructed. See, whatever we have solved in the Jamboot, the same thing, it's done in visualization. We will go for something called tree traversal, which is very important. Is this clear? The pattern which it is constructed, how the elements are inserted, right?
Yes, ma'am.
Okay. So I forgot to tell the main thing, like how to traverse. So after constructing a binary tree or binary search tree, whatever it is, you need some way to traverse and get the records. So we have some three main traversals called Inorder Traversal, Pre-order Traversal, and Post-order Traversal. So if it is in-order traversal, the pattern of visiting the nodes will be left followed by root followed by right. So left, root, right. So in this pattern, we can traverse and get the data. So now just I'm giving the in-order traversal mode. So in-order is left, then root, then right. So this way we can traverse and fetch the data. I will show this and then I will explain. Maybe I can solve. So you just have a look, then I will solve this, how to do this. Okay, now I will explain how it works. Left, so see the algorithm. See if this root is null, it's empty tree, we are not going to do anything. Otherwise, recursively we have to do this. So what is recursively we have to do this? I told left, root, right. So again, if you take from the root address will be the only address that we will be having. In the left hand subtree, again you have to recursively apply this in-order algorithm. Again, what is the algorithm? Left, root, right. So again, go towards the left. So in this fashion, we have to do. So for this example, we are having the address of node 23, for example. So what is left to 23? You have this entire subtree, it is in left. Am I right? So again, 12 will be the address. Again, left, you have 11 and 2. Again, when you go to this subtree, again apply this in-order algorithm. Again, what is the left value? The first element that will be visited will be 2. So that's why we are getting this 2. Is it clear how we are getting the first 2?
Yes, ma'am.
Okay. After that, root. So what is the root value? 11. So that's why we are next element in this traversal is 11. Left, root. Is there any right element towards left? No. So this part is over. So this subtree is now, this is your left. Now what is the root value now?
12.
12. So the next order, the order of traversal, there will be root 12. Now right. So what is the right subtree? Which is 13. Again, there is no, again apply the same, it is null, left and right and null. So it will be 13. So it will be 13. So we have completed traversal of this particular left subtree containing the elements 12, 11, 13. And so this part is over. Now what is the root?
23.
So 23. The next node that will be traversed will be 23. And then coming to the right part, again apply the same in-order algorithm towards the right subtree. So what is the algorithm? Left, root, right. So what is the left? 28. What is the root? 34. So the same, in the same fashion, the elements are listed. Now what is the right? Again, it is a subtree. So again, in this subtree, again apply the same algorithm, left, root, right. So 39, 45, and then 67. Now you can check the order given below. Final in-order traversal order. So this will be written usually in a recursive way. If for every level or every subtree, this in-order traversal will be applicable, right? So now if I want to do a pre-order traversal, so the pre-order traversal will be root followed by left and right. So let me not share the answer, or let me not go for the animation. This is the given tree. You have to traverse this tree in such a way. the traversal order is in pre-order in the sense root, then left, then right. Then what will be the output? What is the first node will be visited in the pre-order traversal? The mode is root followed by left, then right. Root, left, right. So what is the first element that will be visited in this traversal?
23.
23. Okay. Next element?
12.
12.
Okay, 12 is right. In this subtree, this is the root. Okay. The next element?
11.
11. Right. Then
2.
2. Fine. Then
13.
correct. 13. After that, again in the right subtree, apply the same algorithm. What is the root in the right subtree?
34.
34.
34. Then
28.
okay.
45.
5.
Yes.
39, 67.
Yes. Correct. Yes. That's all. These are the mode of traversing the tree. So after you construct a tree, how to traverse it. This is not confined to either in order or pre-order or even the post order that we will be checking. So the whatever answer you told, the same pattern, it is traversed. So after that, the same thing, 34, then 28, then 45, 39, 67. So you can just cross check your answer. So that is right. So it follows a root left right pattern. The post order, the reverse, left right root. That's all. So what is the answer output of post order traversal for the same tree? Post order pattern is left, right, and then root. The same tree, you have to traverse in the fashion of left followed by right followed by root. Is there any answer? Shall I wait or what will be the left right root? That's all. So what will be the left?
12.
2.
11.
Yes. No right. So root 2 and it's empty only. So 11. Okay.
13.
13. Yes. Right.
12.
12 will be the root. Yes. Now coming to this
28.
part. Yeah. 28.
39.
Yeah. Coming left towards the right. Again this right subtree. Yes. 39.
67.
Yes. 67.
45.
45.
34.
34.
23.
20. That's all. So this is your post order traversal. Right. Okay, it is not added in this, but the answer is right. So left, right, followed by root. So why you have to learn all these traversals? See, these are some of the ways to visit the nodes. So given a tree, so in which way I want to traverse. Maybe in this binary search tree, when you check the pre-order answer, you have the pre-order, not pre-order. Let me show the in-order. Looking at the in-order answer, you get a key point, right? When we go for left, root, and then right. So what will be the final output? You can compare the answer. The final answer will be in a sorted order. So given a binary search tree, and if you are going to apply the in-order traversal algorithm, the final output that you are going to get will be the elements that will be in a sorted order. So as in the given output. Maybe in this output, if you check the element 2, 11, 12, 13, 23, so on. Because it is left, root, and right will be having a sorted output for the binary search. Apart from this, we have level order. I can traverse the elements level by level. This is not only the 3 ways. I can traverse the elements level wise. 0th level, 1st level, 2nd level, and so on. So maybe 0th level is element 23. Then the next level, the children of the root node. So 12 and 34. The next level, 11, 13, 28, and 45. Then the next level, 2, 39, 67. So these are the level order traversal. These are the ways to traverse the tree elements. Excuse me. So coming to the coding point of view, just excuse me. I have the code in the code blocks. Let me see. I will copy and paste it here so that it is more visible. Is the code blocks is visible to you, ma'am? If not, tell me. I will just copy this code and I will share in the online.
No, ma'am.
Code blocks is not visible. Okay, I will copy this code just. Anyway, after the session, I will share the PPT and the code, but now I will explain how to write a code. So like we are discussing so far, what is binary search tree, how to do Inorder Traversal, how to insert a node or searching a node or deleting a node or finding minimum and maximum. But coming to the coding point of view, you can easily just write it as a code because you are going to just only recursively do all this operation. That's all. I will explain module wise. It's very easy to understand. Okay, let us say you are going to write a simple C program to perform this binary. Now the online compiler screen code is visible, right?
Yes, ma'am.
So simple binary search tree program. So like you are going to have your header file declaration. Then using the linked list concept, we are going to implement this binary search tree. So when you create a node, now you will be having one data field, right, to store the node value. Other than that, in a normal linked list, what you do, you have a address pointer, right? Struct node star next something you'll be having to refer the next node to store the address of the next node. But here, when you start constructing a tree, you have to, especially for this binary tree, you have a left subtree and a right subtree, right? So you have to maintain two address pointers. So one for your left hand side, left child, and another is the pointer to store the address of your right child. That's all. So we have one data field and we have two address fields, left child address and right child address. So any doubt in the node creation? Just declaration, how to define the node for a tree. For this particular binary search tree, we are going to have a node with three fields here. One is your data field, another one is your two address fields to store the address of left and the right child. Is this clear? First part.
Yes, ma'am.
Coming to the modules. So if we are asked to find this or minimum element or maximum element or to search an element, similarly for insertion, deletion. So module wise, I will explain. Maybe after sharing the code, you can just run this. If you're having code blocks, you can run, or in the online compiler itself, you can run and you can check you can just visualize how the algorithm works. Coming to the search, if I want to search a particular record X in the given tree, okay, what you will pass, I always have the address of my root node. So for any tree, I have the address of my root node. So that address along with the element to be searched, that node value I will pass. The first thing, if your root is null, then also you have to stop searching because it is an empty binary search tree. Or if your root node data field is going to be equal to your search element. So I am having a binary search tree, my search element value, if it is matching with the root itself, then you can return the root and stop the algorithm. Otherwise, if two conditions we check, what we used to check, whether the search element, if it is not matching with the root, either the element to be searched should be less than the root value or greater than root value, that we are going to compare. If the X value, the search element value, if it is greater than your root value, then it is enough to search only in the right subtree. So you need not worry about the left subtree. So if this is the case, again call this. That's why I told this is a recursive algorithm. So what is a recursive function? Calling the function within itself. That is a recursive function. So here we cannot find the answer in one slot. Again, right hand side is again another subtree. It's not a single child, right? Roots, right? You have another subtree. Again, this algorithm you are going to apply for this entire subtree. So you are going to call the same search function by passing the root's right child address. So that will be the new root value, right? Root right child address. So that will be the new root, comma, the element to be searched. So the same algorithm, it will check again. Now, is this data is matching or not? If not, then the element is greater than or less than the root value. If it is less than the root value, search in left half, or greater than the root value, search in right half. So recursively, we have to call. Else, if x value is not greater than root value, then it is understood. Obviously, you have to check in the left hand side. So call the same function, passing the left child address and the element to be searched. Is this clear? See, it's look very simple, because internally when you manipulate, you will be traversing the subtrees and you will be finding the answer. When you write the coding point of view, it is a recursive way. We are just going to call the function by giving the respective address. So that will take care. So recursively it will do whatever the height of the tree. The same algorithm is applicable for every subtree. So we are just going to call the recursively the function. Only thing, we are going to pass the right child address if you are going to search in the right subtree, or if you are going to search in the left subtree, the left child address has to be passed by calling the same function again and again. Is this clear? Any doubt in the search module? Any doubts now? Type in chat. Okay. This is the output of post order. Okay. Any doubts? Able to understand? Maybe for the first time, if you're going to look at the code, yes, I understand it will be like looking difficult, but maybe I will explain. After that, again, if you just have I will share this code also with sir. The same code, if you just have with you, just when you trace how it is working, it will be very easy. Like easily you can understand, right? If you know the concept or the logic behind what you are going to do, then you can easily write in the format of program. For example, already you told me when I gave you the tree, you told me finding the minimum element. Yes, you can do. What answer you told me? You only told me the answer to find the minimum element. How will you find the minimum element in a binary search tree? What answer you told?
Leftmost element.
That's all. Problem is simple. You told you have to have the root address, search towards your left, you will get the find the minimum element. So how will you convert into code? So I am passing the root address. If root is null, it is clear, it is empty. That is empty in the sense you don't have a BST at all. So return null. You cannot find a minimum element in the empty tree, right? So that except that condition you have to check. Else, if root is not null, you have a tree with you. You have a tree with you. So what you told, you have it is enough to find towards your left alone. So here we are not at all bothered about our right hand side subtree. So only left hand side I am going to traverse in order to find the minimum element. So if root left child not equal to null. So why it is given especially not equal to null? If it is equal to, if root's left child is equal to null, then you have to return the root only. There is no left child. So that is the only value you are having. You will be returning. If it is not equal to null, it is understood you have a left side subtree available. Then this is a recursive way. Again, find the element, minimum element, call the same function by passing the root left child address. Now, again, recursively, this function will be called, and this root left child will be your current root. Again, you will check if root is equal to null or not. So in this way, you will be focusing only on your left-hand child, and finally, the value you are going to return, the root value will be the last node that you have visited, that is the left last node of your left side. So that is the minimum value. So that's why it's a recursively we are going to do the same function again and again. So we are going to call the find minimum by passing the left subtree again. Left subtree is again left subtree you will be passing. Then that left subtree is left subtree till you reach the condition not equal to null. You can call this. So when you reach the null, you will be returning whatever the root value you are having that you will return. So that will give you the final minimum element in the given binary search. Same thing if the just change the question. Instead of find minimum, the question is finding a maximum element in a binary search tree. Then how will you change this code? The same code instead of minimum, if it is updated as finding a maximum element. How, where you have to modify?
Right child, ma'am.
Yes, that's all. Instead of left child address pointer, you will be checking the right child pointer is not equal to null. Here also you have to change. Pass the right hand side address value. Then only it will go to the right. It will go to the right subtree again. Recursively, it will find the element in the towards the right, and finally you will get the maximum element which is available at the right of your given binary search. That's all. The codes looks only 2 or 3 lines. If you understand the concept, and you can easily able to write the code. So this and all you know how to create a new node. This already you discussed maybe linked list. Whenever you learn linked list, you know how to create a node, right? You will be creating a node pointer. You will be using malloc function and defining the size of the node to create. You will be getting the data field. You will be assigning initially left child and right child as well. The normal linked list, what you will do, you will be creating the malloc function. You will create a node. Then the data field, you will put the value in the address field. You will, instead of left child and right child, in normal linked list you have studied, you just p next equal to null, you will be assigning. But here we have 2 address pointer. For the node creation, we have stored the data value x in the data field. Initially, you will make left and right as null for the first step, the node creation. Coming to the insert module. Now I'm not going to explain this code because it's very simple. Look at the code. So don't see the program as a big program. Just look at a module wise. Module wise, what you have learned, that is converted in the format of coding. So insert module, what you have learned, to insert a node in a binary search tree, what you will do? If it is a empty, that is empty binary search tree, what you do? You just directly insert a node, that's the root value. Then if the element to be inserted is less than your root, then you go towards the left hand side and you will insert, and or if it is greater than the node value, you move towards the right and insert. The same thing if you want to convert as a code. Look at this code and tell me what you have understood. That's all. What is actually happening here? To insert a record or a data X in a given binary search tree. So we are going to have 2 parameters. Root address I'm having the value to be inserted. Then what I have to do?
If the value to be inserted is greater than the value at the current root, then we are recursively calling the insert function for the right subtree.
Yes.
And else we are recursively calling the insert function for the left subtree.
That's all. Yeah, that's all. Problem is over. If root is going to be null, it is an empty binary search tree. So you are going to call the new node function. In the new node function, you will be passing the x value. Node will be inserted. If root, otherwise, if root is not null, if you have a node already existing, you will be checking the root value with your current element value to be inserted. The same thing, if it is greater than that, you will be calling the insert function by passing your right pointer and the element to be inserted. Similarly, if it is less than value, you have to move towards your left and then you have to insert the record in the left hand side. So this is a recursive function that we are going to use. That's all. Now, what about deletion? Insertion, okay. What about deletion? Deletion only I told 3 cases. I hope you remember the 3 cases we discussed. Case 0, if the element to be deleted is a leaf. Case 1, if the element to be deleted is having single child. Case 2, the element to be deleted is going to have 2 child. So 3 cases we discussed. Case 0, case 1 and case 2. Now, if I want to delete a particular record, a particular data X, from the given binary search tree, we have the address, root address. I have the X to be deleted. Now, what is the case? So if root is null, nothing you can delete, right? It is an empty tree. Deletion is not possible. Just return none. Leave it. Otherwise, if the root x value is greater than root data, okay, the x value is greater than root data, then you have to go towards your right side. So you are going to call the delete function by passing the right child address at x value. Or if the x value is less than root data, it is enough to concentrate on the left subtree. No need to worry about the right part, because the element to be deleted surely would be coming towards the left hand side. So call the delete function recursively by passing the left hand child and the element to be deleted. Right? So after that, so what are these cases? Now you are able to identify the element. So either null case, no, greater than, no, less than, no, because now you identified the correct element point to be deleted. So you are in the correct point where the element to be deleted. You cannot delete as it is, right? That's why I told even first part we have to traverse, like not traverse, that is search. First part, what we are doing, we are searching and identifying the element to be deleted. After getting the correct location, what we have to do, we have to check whether the node to be deleted is having any children or not. So for that, after searching that particular record, you have to see if that road's values left hand child as well as right hand child values are null. So the particular point tells it don't have a left child or a right child, then directly you can call the free method, pass that particular root address, and then the problem is over, the deletion is over. Otherwise, single child scenario. So how will you know it is a single child scenario? Either I can excuse me, either I can have left child or right child. So that's why we have given or, not a uncondition. I don't know whether it is left child. It can have left excuse me, or right. So even any one is true. So even any one is true. So this loop, this condition will be this statements will be executing. So inside that I will be checking if left is null. It is clear I have only right child, so that I am going to store in temp. Or if right is null, then only left child we are going to have, that we are going to store in temp. So we are going to free the root and we are going to return this temp. Why we are going to return this temp? We are going to make a link with the left child or the right child value with the parent. So after removing the element that we want to delete, we have to link it either with the single child. It can be a right child or left child. Only one child link is possible with the parent node. Suppose we have a 2 children scenario. For that one day I told find the minimum element in the right subtree or find the maximum element in the left subtree, any one. After identifying that, we are going to make the problem simple. So here, finding the minimum element in the right subtree, right, for 2 case scenario, finding the minimum element in the right subtree. After getting the minimum element, you have to swap. What we have to swap? We have to swap this minimum element in the right subtree with the node to be deleted. So just root data we are going to replace with the temp data, right? After that, again you are going to call the same delete function. That's all, because we don't know the next case comes under case 1 or case 2. So again, if you recursively call this, automatically again it will go and check whether it is coming in case 1 or case 2, or even case 2, the same algorithm will be repeated. In case of in-order or pre-order or post-order, the algorithm is very simple. Just recursively, for example, if it is to print the element in in-order way, only 3 lines of code. If root is null, nothing to print, right? So only if the root is not equal to null, you have something to print in the tree. Call the recursively this in-order algorithm for the left subtree, print the root data, again call the algorithm recursively for the right subtree. If it is pre-order, how will you change this code? If I'm asking to perform pre-order traversal, this 3 lines, how will you swap? Sorry, how will you change the order? For pre-order traversal, what is the condition? Root, left, right. So first print the data, root data, then call the function of passing the left child address and right child address. If it is post-order traversal, left, right, root. So what you have to give here? Post-order traversal of left, post-order traversal of right child, passing the right child, and then print the root data. That's all. So I will stop with this. If you have any other queries, you just let me know. I will share this tree question, sorry, PPTs and the code also. You can run this once, you can give some data, and you can just explore the working. Any doubts? Okay.
Ma'am, what's the use case of in-order and pre-order and post-order traversal, ma'am?
Yes, ma'am. For in-order only I told, right? Suppose given a binary search tree, in-order traversal will always give you the elements in the sorted order. Maybe the use case where you want, given a tree, I want the records in the sorted order. Directly you can go and use this in-order traversal. In-order traversal will give you only sorted order for the binary search tree problem that we are discussing now. Left, root, right concept. And also it is not necessary you have to always see, these are the ways to traverse in order or pre-order, post-order. It's not necessary you have to always confine with these three orders. That's why I told. Sometime for the use case you may get, I want to traverse the elements according to the level wise. Then you have to go for level wise traverse also I told, right? The first element, then you have to second level elements I want to fetch, then third level elements. So depending on the case, you can go for level order traversing. Or the other case, for example, I'm telling, I want to this traversal like a BFS or DFS algorithm, breadth first search, depth first search application, where you want to start from one node. I have to visit all the nodes in that path, and then I have to backtrack, and then I have to go to the next path. So for these kinds of procedure, we can go for DFS, depth first search. So many things available. Maybe one use case I will tell for DFS. You just think on that. Okay, you are aware of this n-queens problems, right? If not, I will give you a use case. Given a 8x8 board, okay, 8x8 board. You want to, or 4x4, any n-cross-n chessboard, something like that. Okay, either it can be 4x4 or 8x8 or 16x1. You want to place the queens in that particular board in such a way you don't place in the same line. Okay, like you know the conditions, it should not be in the same, you cannot place it in the same row because it will again the chess concept, you cannot place it diagonally. Okay, or you cannot place towards the right. So you have to see all these conditions, you have to place accordingly. If you are going to insert these kinds of problems using this particular algorithm, I can start traversing, I can go towards one path. This is depth wise. If this is not satisfying, again I have to come back and I have to take the next level. So this kind of problem you can go in a depth wise manner using the depth wise search traverses. Is it clear, ma'am?
Yes, ma'am.
Any other questions, ma'am? So the main objective of learning this entire session, this free session. So any problem, not telling this or that, any specific application, any scenario given, if you're able to represent in the format of tree, you know, like what is the advantage of using it, so how will the time complexity login. So what is the learning of this, why you have to learn this BST or why you have to learn this AVLT. So all the purpose of learning this is, everything has your pros and cons. You may tell like, yeah, BST, you know what is the advantage, like you are finding towards one search space. So there are some constraints like skew part. So if it is the skewed one, then how we can overcome, you have to balance it. So once it is balanced, we have methods to balance. And if it is after balancing, you can make sure that you are going to get the operations, like data structures operations that can be done in your log and time taken. So then apart from that, You have other, I have not told everything in trees, but you can just see, I have, apart from that, you have many splay trees. So if I want to identify the recently accessed records, maybe like any search operation you're doing, I want to always have my recently visited node to be at the top. So the next time I want to visit, I can just fetch the node in O of one time. Then you have the concept of splay tree. Similarly, we have B trees, like B trees in the sense like if I don't want, I want to reduce the height of my tree, right? I don't want to fetch go long way. I want to reduce the height. Then we can go for B tree, which is going to be otherwise it will be a very big tree where we'll be accessing the elements. So these are some of the variants of your trees. Okay. If no more doubts, then we will stop and stop sharing. Sir? Questions, sir?
Hello, ma'am.
Yes, ma'am.
Okay. Thank you, ma'am. The talk was very good, ma'am. I think students would have benefited from this. Thank you, ma'am. Ma'am, can you wait for a minute, ma'am? I'll just try to call sir. I don't know whether.
Yes, ma'am. Yes, ma'am.
Yeah, sir is available.
Ma'am?
Sir?
Session over, ma'am. Completed?
Yes, sir. Yes, sir.
Okay, madam. Students, any other clarifications? Okay.
Yes, sir.
Dear students, any other clarifications, doubts? Shall we end up the session?
Yes, students, if you have any other queries, you can let me know.